The last part of kinematics in 3 dimensions is looking at the acceleration. Acceleration, like we've seen before, is the rate of change of velocity, how much the velocity is changing per time at an instant, and an instantaneous rate of change is a time derivative. So acceleration is the derivative of velocity. Since the velocity is a vector with several components, the acceleration is just the derivative of each of those components separately. It's the first derivative of velocity, or since velocity is already the derivative of position, acceleration is the second derivative of the position with respect to time. When you're looking at an acceleration vector on a curve, the acceleration vector always points inward on a curve on your trajectory, and the acceleration is going to be measured in meters per second squared or feet per second squared. There's also average acceleration. Average acceleration is looking at the average rate of change of velocity, so it's the same idea, but instead of looking at the little tiny change in velocity during a instant or a little tiny change in time, we're looking at a finite change in the velocity during a finite change in time. Since the velocity is itself a vector, we're going to look at the change in each component of the velocity during that finite time interval. Another way to find the average acceleration is by using the average value theorem that we've seen before in Calc 1. And in this case, we are adding up the acceleration at each instant during that interval. We add up the acceleration at each instant. We divide by the number of instances in that time interval, and that gives us the average acceleration over that interval. And again, notice if you integrate the acceleration, this gives you the change in velocity, and the change in velocity per time is another way of expressing the average acceleration. So these two ideas, again, are two versions of the same thing. What the average acceleration is giving us is the difference between v initial and v final in an amount of time. So imagine we know the initial velocity and the final velocity. I could take the initial velocity here, and I would sketch, this would be the negative v initial. And so vf plus a negative vi would give us what the acceleration is at that instant. And a couple things here. Notice that the velocity vector is a little bit shorter there. It's a little bit longer, so we're speeding up, and the acceleration is in the direction of motion, causing us to speed up. Also, we are turning to the right, and the acceleration is pointing in that direction as well. We can also find the velocity from acceleration. Acceleration is the derivative of velocity, so velocity should be the antiderivative of acceleration, and it is, kind of. If we integrate acceleration, we're going to end up with a plus c, and we need an initial condition. We need an initial velocity to be able to find out what the velocity would be at any point in time later. And again, note when you do the definite integral is measuring how much the velocity changes per time. When you add up with your integral all of those changes in velocity, you get the overall change in velocity during that interval, not the actual velocity at the end. This is giving you the change in velocity, and you'd have to know your initial velocity. You know the change in velocity, that's this expression, but you also need to know the initial velocity as a vector to be able to find the final velocity at the end of that interval. And then lastly, we've talked about whether an object is speeding up or slowing down. Speeding up and slowing down is something different than having an acceleration. Speeding up means the magnitude of the velocity is becoming larger. The speed is the magnitude of the velocity, and the speed is becoming larger, or the speed is becoming less, the magnitude of the velocity is getting less. That's different than the acceleration. Acceleration is measuring how the velocity changes at a given instant. So our velocity vector has two parts. It has a magnitude or direction, and a change to either of these quantities is going to count as an acceleration. So we can think of our velocity vector and our acceleration vector can be arbitrarily in 2 or 3 dimensions. And we can think of the acceleration vectors having components. We don't care about the x and y components necessarily, but we care about the component that is parallel to the velocity, the component that is in the direction of the velocity, and the component that is perpendicular to the velocity. So this parallel component of the acceleration controls the speed of the velocity, the magnitude of the velocity. So if the acceleration is less than 90 degrees, if they're mostly in the same direction, that means that the acceleration and the velocity are in the same direction, which means you're speeding up. That parallels what we saw for kinematics in one dimension, but in that case, the velocity and the acceleration could only point to the left or only point to the right. In this case, they could both point in arbitrary directions. If they are less than 90 degrees apart, they're mostly in the same direction and they're speeding up. If they are more than 90 degrees apart, they're closer to being anti-parallel, and that means that they're slowing down in that case. There's another component of the acceleration, though, a component that is perpendicular to the velocity. And if this component is perpendicular to the velocity, it can't affect the magnitude of the velocity. It can't change the magnitude. So this perpendicular component here is controlling the direction. If you have a perpendicular component here, that is going to pull the velocity this way, and you can sort of imagine the trajectory would curve to the left from the point of view of the object. If you have a acceleration that is perfectly aligned with the velocity, there's zero component that is perpendicular to the velocity, and that means that we're changing the magnitude. We're slowing down in this case because we're anti-parallel, but there's no change in direction in this case. The particle is going to continue moving in a straight line at a slower speed.